und hatte also ein bisschen Fragen, wie die weiteren Pläne jetzt sind Richtung.
Das sollst du mich gerne einfach anschreiben,
ja.
kein Problem.
Wir wissen nur nicht, wie der Plan bei uns.
Gab es hier spezielle Zugangsdaten zum BSC ENES HPC oder? Gab es hier irgendwie spezielle Zugangsdaten?
Bei mir hat er sich automatisch ins EDU-Room eingewählt.
Probier ich das mal direkt.
Ansonsten hängen da an den Säulen.
Okay, everybody, we are going to start the next session that is going to be the last one of the day, quite a long day in fact. We prepared the session with Peter Dueben and Balaji, whom you can see on the screen. Hi Balaji. And myself. Peter Dueben will be a speaker, invited speaker at the beginning of the session, and Balaji and myself will share the session. Balaji will mostly concentrate on the questions arriving on the Google Doc, while I will try to see if there are questions coming from the room. Okay, so the aim of the session is really to look at recent developments where traditional modeling of climate or meteorology is associated with more recent machine learning issues or modules or emulators or whatever. So that's the whole purpose of the session. We have a number of speakers who are from overseas, from California mainly. That's the reason why we had to schedule this session quite late in the afternoon. But even the European speakers could not make it for different reasons. So that's going to be an entirely remotely, with remote speaker session. So, Balaji, unless you want to say something? If not, we go ahead and your microphone is not open.
I will monitor the Google Docs and please go ahead and we can start the talks.
Okay, Peter, are you with us?
Yes, I am. I can hear you and see you. Yeah.
So every talk is scheduled for 20 minutes plus 5 minutes questions. But talk by Peter because he will also probably report from a recent workshop that they had at ECMWF, so he is given a bit more time. So you have 25 minutes plus 5-minute question. Peter, the floor is yours.
Thank you very much. Yeah, I'm very, very sorry that I couldn't attend. I would have loved to come to you guys and see all of the faces again. But I just moved to Bonn 2 weeks ago, and everything. The dust still needs to settle for the family moving and everything. So therefore, I can only participate remotely, unfortunately. I was asked to give you an overview of basically what machine learning is at the moment in general, and in particular to summarize some of the results we had at a workshop a couple of weeks ago. Oh, no, that's a couple of weeks ago, yes. So machine learning for weather and climate predictions in principle. We should start with the question why we should look into this right now. And as I said, this is kind of an overview slide, really. One of the reasons why we should look into machine learning is this kind of extreme rise of the amount of data that we work with. So on the slide on the right, you see basically the time in years over the last couple of decades. And on the y-axis, you see the compute performance that we had. And the different boxes here are the different supercomputers that we worked with over the years. And you will see that basically the orange line here is increasing with the boxes, which is basically giving you a linear increase of compute power over the years, which results in an exponential growth rate because this is a logarithmic scale. Everyone knows this, it's kind of Moore's law, well known to everyone, but what's kind of often really not thought about so much is actually the data archive size that has been growing at the same pace. Or well, at least also exponentially. So there's a blue line in here as well, which is giving you the size of the data archive in ECMWF, and it's also a linear growth rate, so also an exponential growth in time, basically. So bottom line is we have a huge amount of data that we need to look into. And machine learning can potentially help to look into this data. Second point is the compute hardware. So I've stolen this slide here from Thorsten Höfler, where he tried to basically collect all the different hardware companies that are investing into hardware dedicated for machine learning only. And you will see that there are quite a number of companies on there and quite a number of very well-known names. And basically the bottom line here is that this is a multi-billion-dollar industry, and it's kind of dwarfing all other HPC developments right now. So even if you're not interested in machine learning, you should be interested in how you can use this machine learning hardware for your purposes. And the hardware is going to be optimized for low numerical precision and high throughput rate in terms of flop rate. So there's a lot to come in terms of high-performance computing hardware for machine learning. Point number 3 is that there's a lot of software developed at the moment. And in particular, there are tools like TensorFlow and Keras that actually allow you to write very powerful machine learning codes with just a couple of 100 lines of Python code. So it's not the same way as kind of we develop typically our models with Fortran and millions of lines of code. It's actually a domain that can move very, very fast because it has very efficient software that allows you to write, very high fidelity code with just a couple of 100 lines of code. And then finally, the increase in knowledge. So we're talking about 100 papers coming out every day on machine learning and artificial intelligence. So we are now know much better how to use very dedicated tools for specific domain applications than we knew, for example, 10 years ago. Next point is why should we work with machine learning in our system sciences? Basically, mostly what we're talking about is what we call supervised learning. So you have input fields and you have output fields, and you basically learn the mapping in between using machine learning tools. And why would this be useful? Because the system that we're looking into, the Earth system, is really very, very difficult. It's very, very large. So basically, we are only working with very coarse resolution models in principle. The important processes need to be parameterized, like clouds, for example. The system is chaotic. It's complex with a lot of components interacting with each other. So this means that there are it's kind of quite a troublesome domain if you want for normal conventional modeling. And on the other side, we have a huge amount of data about this Earth system. So at ECMWF, we have hundreds of petabytes of data, and we're talking about observations and also model data at the same time. And if you now put those two things together, you have a tool that actually can extract knowledge from data, and that's kind of very much high performance on high performance computers. And you have a very complex system with a lot of components that are not all understood very well. And then it's kind of quite clear that machine learning as such a tool will actually help you for many application areas in Earth system sciences. And what is the perspective right now? So I like this tweet from David John Gagne, who is kind of one of the leading machine learners at NCAR. And he basically mentioned that in 2016, machine learning was considered as a black box application that can't really learn physics and therefore not really very promising for system modeling. And in 2022, you have slides like this one, which is a slide from Dale Duran, which he presented at the AMS conference earlier this year. And he's basically asking the question like whether we should replace the entire dynamical core with machine learning tools. And that's quite a statement in general, but in particular also because Dale Duran is kind of the author of this very famous book here that is basically developed and used by a lot of people who are actually learning about dynamical core development in principle. So there are quite powerful people who really think that machine learning can make a big difference in the domain. And on the other hand, there's also this guy here, Jensen Huang, who has recently given a keynote talk at the GTC conference, basically the big conference of NVIDIA. And Jensen is a CEO from NVIDIA, so he has something to say there. And what he's basically stating is that the last revolutions in high-performance computing were basically about single-threaded performance in the 90s. Then you had accelerated computing and scale up and out lately. And now basically we're talking about new revolution from machine learning, where this will really transform high-performance computing in principle. And he's giving the specific example of ForecastNet, which is basically nothing else than a global forecast model trained on machine learning. And Karthik is going to talk about this later on. So basically, there are big players in the field who really think that machine learning can make a difference. And whether this is also possible for climate, it's a different story, but we will learn more about this later on in the session, I guess. So another point to be made is kind of where we are at the moment is that we also still want to learn how to use the magic of machine learning for our domain. So how can we actually kind of build customized tools for machine learning that can really be transformed also in our specific domain of system sciences? And I just brought you this example here. In the atmosphere, you have all sorts of different length scales that are working with, that are interacting with each other. So on the x-axis here, you see all sorts of magnitudes of orders of magnitudes of the length scales in meters. And on the y-axis, you see all sorts of orders of magnitudes of the time scales in seconds. And you have all those different features of the atmosphere that are kind of need to be represented one way or the other if you want to make a good weather or climate prediction. And on the other hand, you have machine learning solutions that can actually take care of some of those interactions between scales. So there are tools, for example, that are called encoding decoding networks. And what's happening here is that you have a neural network with a couple of deep layers of neurons here. And you basically have a high resolution input level on the high resolution output level. And the intermediate levels of the neurons basically are reducing in the number of degrees of freedoms until you have something like which is called the code or the latent space with the smallest amount of degrees of freedoms. And it turns out that you can, in principle, use these kind of structures to also learn some of the scale interactions that we have in the atmosphere. So you can actually make use of those very complex machine learning techniques in a sense that they can tackle some of the problems that like conventional tools are struggling with, like, for example, scale interactions. And there are a couple of people working with those encoder and decoder networks for atmospheric sciences. But I give you just one example that we were looking into. So we were basically using so-called conf networks that are doing this encoding and decoding in both space and time. And the idea here is if we do downscaling from a model simulation at 6-hourly time windows to kind of total precipitation field from observations in daily output. So the x-axis here is time. And we basically kind of just coarse grain from 6-hourly to daily, and then from daily to weekly, and then back on daily. And we kind of get better results than if we would basically just do the mapping at the same level of resolution. So there's some hope basically that you can get better results if you combine machine learning tools with some of the domain-specific problems. This is just an overview slide where people are looking into right now with machine learning for system sciences. So some applications are in the sense that we try to improve our understanding of the Earth system. So what we can do here is we can, for example, take different sources of data sets and use machine learning to map between one source and the other. And this will help you, for example, to fuse information content and to kind of close gaps in data sets and all these kind of things. Then we can do so-called unsupervised learning, where we basically just throw a lot of data into the mix and we try to understand the dependencies within the data, like, for example, with principal component analysis or these kind of things, or clustering techniques. We can do causal discovery, where we try to understand how the different features in the Earth system are connected to each other. We can do AI-powered visualization and also a lot of uncertainty quantification. So machine learning turns out to be very good actually in doing uncertainty quantification. Then we can speed up simulations, for example, via the use of emulators. So you try to learn model components by machine learning and replace them to be more efficient. You can port emulators to heterogeneous hardware. You can reduce numerical precision and use kind of sparse machine learning to really go towards green computing and to make the efficiency as good as possible. You can try to optimize your high-performance computer workload and the data flow workflow and these kind of things. You can do data compression and so on and so forth. Then you can improve models. For example, you can try to learn model components from observations. You can try to correct for model biases of the models and learn errors. You can do quality control of observations and observation operators. And also you can do things like feature detections within the model simulation. So people are, for example, trying to detect tropical cyclones within data sets. And then finally, you can also link communities with machine learning. So you can, for example, if you have your favorite health problem and you have a long data set of health indications, for example, over Cologne or something like this, and you also have weather data, you can easily link the two data sets with each other by just learning the mapping between the health data set and the weather data set. Or the same is true for energy, for example, for the power production of local wind farms. You can do it for transport. If you, for example, want to learn about icy roads, surfaces, these kind of things. You can use the data from the cars directly and relate them to the weather data without a direct understanding of the link. You can think about pollution application, extremes, and so on and so forth. So there's a lot in principle to be done with machine learning. And this slide is kind of more ECMWF focused. So this is a workflow that we have at ECMWF where we collect observations. Then we do data simulation where we bring the observations and the model simulations together to generate initial conditions. Then we have the numerical weather forecast to look into the future. And then we have post-processing and dissemination where we basically kind of just distribute the results, and underlying this high-performance computing and big data processing infrastructure. And I've asked around at ECMWF to just learn where people are using machine learning at the moment, or at least planning to use machine learning. And this was kind of the answer. So each of those boxes is one of the application areas where we think machine learning can make a difference, or at least should be explored, and to see whether it can make a difference. So the bottom line is there's not only the one application for machine learning in our domain, but it's really that there are a lot of applications, like order of 30, for example, at ECMWF. And that they're distributed all over the place. So it's not just observation or just numerical weather forecast, but it's really all of the components are investigated at the moment. And it's kind of we're still at the phase of like really understanding where in this workflow will machine learning really make big differences and where are our conventional tools actually more competitive. Just a couple of words on the challenges that we have. So if you have the three communities here, machine learning, high performance computing, and weather and climate modeling. So where are basically the challenges for machine learning right now? The first of them is that often there are different philosophies between domain scientists to try to understand physical reasoning and physical feedbacks, and machine learning scientists who typically view this as a machine learning problem with the input-output loss function type thing and are basically trying to reduce mean errors. And often these two communities clash to some extent, and we will, I'm sure, have an interesting discussion also and at the end of this session after the talk that will follow after mine. Also, the tool sets are different on both sides. So the machine learning side is basically Python and GPUs, where the weather and climate community is still working with Fortran and CPUs. So there's also a bit of a potential clash to some extent. So we need to bring the communities a bit closer together. The second point is that off-the-mill machine learning tools are often not sufficient for our physical fields. So we need to think more about physical reasoning in our machine learning solutions and basically try to combine our knowledge about the Earth system with the machine learning developments. Then the integration is often difficult, so it's not that easy often to kind of combine machine learning tools with the conventional workflows. We're still also in the beginning of scaling up our efforts towards petaflops with our machine learning applications for our domain. However, Karthik, I'm sure, is going to talk more about this and show you some results, how far we can go right now. And also, we have a problem with reliability often. So for weather and climate applications, these applications are really meaningful for society. And they just should not go wrong. So we have a problem of using a black box tool that we can't really trust in a lot of aspects, because we basically, there's a bit of I can hear some voices. Maybe that's from the audience, I don't know.
Yes, anybody who's talking, please mute yourself.
Yeah.
Thank you.
So reliability is also a problem and ethics of machine learning tools in principle. So I was asked to talk about a bit of the results of the workshop that we had recently at the beginning of April. And we had basically 5 days of one day for multi-stream dissemination workshop and 4 days of the machine learning workshop. We had, I think, 450 people registered for both events. And we had a lot of discussions going on, a lot of fantastic speakers. What I decided to do was basically, I have one slide examples for a couple of talks that I handpicked, basically. Obviously, this doesn't cover the entire workshop, but the good thing is that if you go to this page up here, or you can also find this by the normal ECMWF page, then you will also find all the recordings and the slides for all the sessions and all the talks. So I can really, if you find something interesting, just go to the webpage and have a look. So the first talk that I wanted to talk about is a talk by Ryan Keisler with the title of Forecasting Global Weather with Graph Neural Networks. And the idea here is basically, that's one of those talks that we call a weather bench type problem. So what we do here is we basically take reanalysis fields like ERA 5 fields globally, and then we just learn the mapping between some state in ERA 5 and some state in the future. And by doing this using machine learning, you basically are able to learn a forecast model. So you can basically just build a pure machine learning model that can do a forecast for global weather and for the future. And Ryan it's kind of one of many papers on Weather Bench, but he kind of made a big step here because he basically extended the normal standard data set that we were working with. He worked with 1 degree resolution, but he had 13 pressure levels in the vertical, so way more than others in the field. And he was also working with 3 hourly time steps, so a higher temporal resolution as well. And he used 6 fields per grid point. So he had a lot of fields in principle. And he also used what we call graphical neural networks. So the idea here is that you don't basically just use longitude latitude grids, but you actually work on the model grid, or an unstructured grid at least, and kind of learn how to do the mapping from unstructured grids via a structured state in the middle to an unstructured grid. And those 2 points combined basically led to quite a significant improvement in the result that definitely surprised me. How good the quality of the network at the end was. And basically for some of the leading features like Z500, temperature at 850 hectopascal, R700, and so on and so forth, you actually got results that were at least competitive to the GFS model and to some extent also competitive with the ECMWF model. Fair to say that this method is still kind of smearing out in the longer term, so I wouldn't be too bothered by basically ECMWF being beaten by the model here, for example, but still quite an impressive result in principle for a machine learning method. The next talk was by Jussi Leinen, and he was talking about time-consistent downscaling of atmospheric fields with generative adversarial networks. And the idea here was that the input was basically precipitation fields over the Switzerland, and the precipitation observations were available at high resolution, and he coarse-grained the field and then tried to learn the mapping from coarse to fine grained. So he basically did a classical super resolution exercise. And what he was doing here was using so-called GAN networks. And those GAN networks are basically not just one neural network, but there are two. So you have one neural network that is the so-called generator. So you give the coarse resolution as input and also give an input noise. And then the generator will try to reproduce a high resolution model, the high resolution sample. And then there's a second network called the discriminator that will try to basically take the result from the generator or a real sample from the dataset at high resolution, and will try to understand, to distinguish between which one is the real one and which one is the generated one. And you have the two networks that are kind of working against each other. And by this competition, you basically manage to get very realistic results and samples in principle. So if you get data samples like this, where you have basically the precipitation observation over Switzerland, and you have the coarse-grained result, and then the GAN is basically producing yet again a very realistic pattern how the precipitation field could look in principle. So that's very nice work. And it was kind of extended a little bit by the talk from Lucy Harris, where she looked into a machine learning approach to stochastic downscaling of precipitation forecasts. And the difference here is now that the input is not also an observation coarse-grained, but it's basically the model simulation of the IFS at 9 kilometer resolution. And the output is now a precipitation over observation of at 1 kilometer over the UK. So it's kind of a similar step to what Jussi has done, but now also with a forecast error. So IFS is not going to be very great in the sense that the precipitation field is perfect, because it's going to be model versus observation rather than just coarse-grained to fine-grained. And she also produced quite nice results. And in particular, the interesting part is that with those GANs, you can actually just use different random seeds, and you will generate an ensemble of predictions for this mapping procedure. So you have IFS prediction on the top left, you have the ground truth over the UK, the Nimrod data set over precipitation on the top left, bottom left, and you have one realization of the GANs, and you see that this is kind of quite a realistic feature for the precipitation field, but you can also generate like 50 members of these GANs. And then you can basically have an ensemble, and you can make a mean prediction of this as well, generating like also kind of ensemble type predictions. So you also get an uncertainty quantification with your mapping. And there's also the talk by Zuman, who is in the call right now, and is also going to talk a lot about generative modeling, I guess, for nowcasting applications later on. Then there was a talk by Tom Beugler. Tom has recently moved to Switzerland, so back to Europe from the US. So if you were searching for a good seminar talk speaker, then invite Tom. He's great. So Tom was talking about climate invariant, causally consistent neural networks as robust emulators of subgrid-scale processes across climate. And this is kind of one of the papers where people are trying to emulate model components. And in particular, Tom tried to basically take the input of a physical state of a climate model and try to predict what the superparameterization model would actually give you as its physical tendencies. So superparameterization models are basically running cloud-resolving models within every grid cell of the big model. And this increases the computational cost by something like a factor of 20 or so quite significantly. However, it's also known that it will improve your results, in particular for the tropics and precipitation fields. So the idea is now to basically try to mimic this CRM model tendency, so the superparameterized tendencies, basically getting the benefit of the superparameterization for free using machine learning. And this is kind of not the first study and not the first talk about this. So there has been a paper by Tom from 2019. And what they basically found was they could really, really represent those physical tendencies quite well, and well enough to actually reproduce the benefit from superparameterization in your coarse resolution models. But when they basically change the climate, you get disastrous results. And the reason is because those deep learning solutions are basically failing always to extrapolate into unseen data sets. So if you've changed the climate, you will get weather situations that you have never seen before. And then the neural networks will fail to extrapolate and do all sorts of mess and will basically break everything. So therefore, this never really worked for the changing climate. And now Tom basically gave a talk about how you could fix this problem, and he gave a couple of suggestions. One of them is that you could simply change from your prognostic variable from specific humidity to relative humidity, because then you would change from a value that could really just grow and grow and grow in specific humidity to relative humidity, where the value would basically stay always similar between 0 and 100%, I guess. So this already helped, but he also gave some solutions, some further ideas using causal discovery and other things. The fifth talk is by David Laundrie, and he basically was one of the participants of the WMO challenge for S2S. So there was a challenge a couple of months ago where we basically tried to collect entries where people tried to improve S2S predictions with machine learning. And there were a couple of the winning teams presenting at the workshop, and David was kind of the #1 team. And a long story to go into all the details, but what I wanted to stress for the talk was that I was really impressed how he basically built a solution in the end that kind of took the input of several different forecast products, so ECMWF, ECCC, NCEP, and so on and so forth, did some post-processing on those tools, and then mixed everything into kind of a deep learning tool as well, also using the features of the ECMWF forecasts, and then basically learned the anomalous prediction of from the reference simulations that you had at hand. So basically he was combining all the information he had from climatology, from the different forecast centers and so on and so forth, and were then able to actually, using machine learning, steer everything up in a way that they actually kind of got some results in the end that were improved. So quite interesting way of combining information here. Then the sixth talk is from Jonathan Wade, and he basically looked into the improvements of ensemble predictions. So here the input is ECMWF ensemble forecast, and the output is also ECMWF ensemble forecast, but in an improved way. And this is based on work with so-called transformer networks, and this is kind of also based by work by Tobias Finn, who was at the time a PhD student in Max Planck in Hamburg, who was the first one to use transformer in this context. And transformer methods are really coming from natural language processing. So they are basically used lots to kind of translate from different languages, for example, text. And in a sense, they are very good at relating different words and sentences to each other. And this comes back to my slide earlier that you use encoding decoding networks, for example, to represent scale interactions, because you can use those magical tools from machine learning also in a magical way in weather data. And in this case here, you actually use this tool that's coming from natural language processing that is relating the importance between different words and sentences in a sense that they actually relate the importance between different ensemble members in an ensemble forecast, and you can actually improve results with this. And you actually really get better results. So this is a CRPS. So the lower the better, and this is for temperature at 2 meter. And you basically, the black line is a reference ensemble. The blue line is the benchmark with the kind of conventional tool, and the red and orange ones are the lines that we get from the machine learning tool. So we kind of get really improvements using this method. Okay, the last thing that I wanted to talk about is the example talk by Karthik, but there's no point in talking about this one because he's going to talk about this himself at the end of the session. I'm going to skip these 2 slides because I'm running out of time, but just the one thing, I think this is still the single most important development that we need to achieve in the kind of mix between the communities of machine learning and Earth system modeling is that we still have the domain scientists who are kind of defending their ground quite fiercely. And you have the machine learning scientists who are kind of a bit leisure and a bit, well, maybe too optimistic sometimes. And basically what we still need to do is to kind of blend those 2 communities. So we still need to basically make sure that we will end up with machine learning domain scientists rather than just domain scientists or machine learning scientists. Okay, the last slide, which is kind of the summary. Where are we going to be with machine learning in 10 years from now? So basically, just imagine a world where we kind of go towards the ability to collect and centralize most of the data set that we have right now, including observations and model and reanalysis data, and put them all into one data storage system, basically. And then imagine that you have mapping tools that can basically map between these all these different data sets in a quite automated way, so that the individual scientist doesn't need to learn everything from scratch, but can actually use standardized tools. And imagine that we could also interpret those tools using, for example, like physical consistency tests and these kind of things. And imagine that we also could estimate uncertainties for all those data sets by basically relating the data sets to each other and learning, for example, when observations were clearly wrong because they are totally different to what we get from analysis from weather predictions. And then also imagine that we basically have AI-powered fly-through visualization tools, and then finally also scalable tools that you can really just start from Python or Jupyter notebooks and run them on or petabytes of data on a petaflop supercomputer. And if we reach this point, we can really make a big difference with machine learning, I'm pretty sure. And with this, I want to thank you for your attention.
Thanks, Peter. We have one question on the Google Doc, but it's from Luis, and Luis is in the room, so maybe it's better for Luis to rephrase this question.
Okay, it's a pretty simple one. It's a fundamental mathematical one. That you have a domain of definition and you have a domain of value. And the machine learning system can only map one to the other from the learning process. So if you have an exceptional event, which your model itself could do, but it never happened before, so the system didn't learn it, and it will not show you as a value. What's about that? And that's especially in the area of disaster prevention, because that's usually happen when something exceptional, and that's really kicking you in the... So that's a fundamental problem, I think. And how would you react on if you would get a director of a new forecast center and say, okay, I'm going with the machine learning and only do AI-based forecasts, and then you have 100,000 victims in a natural disaster?
Yeah, so I raised this point. I mean, earlier I talked about this kind of reliability problem, and that's exactly the point that you are rephrasing here. So we know that deep learning tools are quite bad in extrapolation, and we know that if we train from nowadays climate, we will not necessarily have a good tool working in future climate, or already for weather forecast, it could happen that just the 1 in a million years event would basically kick off the machine learning model in principle, right? This is a problem. However, on the other hand, also a lot of people are looking into this. So I gave you the example of Tom Beukler, where he basically presented, I think, at least 2 potential solutions to kind of address this point. But there's more work to be done. There are a lot of people working into it. So there are, for example, in the US, there's an entire, I think, a $20 million project looking into basically machine learning, which is trustworthy and then basically also physics informed. And there are interesting ways how to combine machine learning with the real world, but it's something to be aware of. I don't want to diminish this point. It's an important point to look into.
Okay, thank you again. And we now proceed to the second talk in the session by Fleur Couvreux. I guess she's online. And she will report. Yes, and you will report on the iTunes Explorer. I give you the floor.
Okay. Can you see my screen?
Yes.
Not yet, but it will come.
Great. Okay, so tell me when I can start.
I can see it.
You can.
Okay, so I can start?
Yes,
Yeah,
please go ahead.
Okay.
Technical staff
So
say it should appear very soon. So.
So I'm Fleur Couvreux from. Can you see my slide, or because I cannot know if
Yes.
my slide?
I can see it. I'm on Zoom. I don't know if everybody can see it in the room.
Your screen is your slides are on the screen now. Go ahead.
Okay, thank you. So I'm Fleur Couvreux from the Research Center of Météo-France, and I'm happy today to present you the iTunes Explorer, a calibration tool to accelerate model calibration based on process-oriented metric. It aims at harnessing machine learning for model development. And so this tool has been developed thanks to a close collaboration between experts from atmospheric processes, model developers, and applied mathematicians. This tool actually strongly relies on the comparison between high-resolution simulation, called large eddy simulation, and single-column version of 3D model using a statistical method imported from the uncertainty quantification community. So in this presentation, I will first explain you the main motivation for the development of this tool. I will then describe the tool and show you 3 results to illustrate the potentiality of this tool before to conclude. So an atmospheric model used either for numerical weather prediction or climate projection purposes encompasses a dynamical core that solves a discrete version of the fluid dynamic equation and parametrization that arise from the fact that most of the physical processes cannot be explicitly resolved. In particular for global models. The parametrization actually compute the impact on resolved variables of thermodynamical processes, radiative processes, chemical processes, but also dynamical processes that occur at scale smaller than the computational grid. And so this parametrization reflects our process understanding, and they are submodel, and they involve 3 parameters that are indicated here by lambda p that need to be calibrated. And in fact, these 3 parameters arise from the fact that we have simplified the complex nature of all the subgrid processes. And so in the development of those parametrization, we have strongly used the comparison between single column model and high resolution that serve as a reference. And we propose to exploit this framework also not only for parametrization development, but also for calibration purposes. And in fact, the calibration of those parameters is a complicated task that is scarcely documented. And it's actually achieved both first at the parametrization level during its development, but also through the calibration of the global model to verify some constraint on the energetic budget or on performance curve. And in particular for climate model, it often involves radiative metrics. This is a key step for model development that has only recently been documented, and it often realized through an optimization procedure that aim at searching optimal values of the 3 parameters, and this may lead to some overconfidence. So our approach is to build a calibration tool that serves parametrization development based on the LES single column model comparison. So this will induce a strong process-oriented focus on the calibration. We propose to use methods of the community of the uncertainty quantification, and in particular, we have based our tool on the history matching developed by Daniel Williamson from University of Exeter. And in fact, the important approach is to be able to tackle jointly calibration and parametrization development together. Before to go on, I just want to take a minute to explain you the advantage of the framework of the single column model LES comparison framework. The single column model is actually an extraction from a 3D model of a single atmospheric column that actually integrates the same suite of subgrid parametrization. So boundary layer scheme, shallow cloud scheme, convection scheme, radiation scheme, etc. But is run in a constrained large-scale environment. In fact, the dynamical core is replaced by a forcing term. What is nice with the single column model is that it's very cheap, but still is representative of the main biases of 3D model. And this framework has largely been used for model evaluation and development, in particular by the GCSS and GAS community. And actually, because on the 1D, you mainly only have the parametrization that are active, it allows you to really do a focus on the parametrization, as there is no link with the large-scale dynamics. And eventually, the LES has been shown to be nice references, especially when you focus on boundary layer processes and cloud, and because you get a 4D field of a lot of variables, you can compute a lot of parametrization-oriented diagnostic. So now we'll detail the calibration tool. In fact, with this tool, what we aim at is to define the subspace of the parameter value for which the single column model will match the LES on selected metrics for a series of cases within a given uncertainty. So to do so, we use the history matching with iterative refocusing approach proposed by Daniel Williamson. And so what we do, it's actually using machine learning approaches for tuning. So how does it work? So first, we need to select the metrics that we will use to calibrate our model. It can combine different cases and different metrics. We then need to identify the three parameters we want to calibrate and their a priori range of variation. So let's say we have 10 parameters. We are now an input space of 10 dimensions. In this parameter space, we will sample a few values on which we will run the single column model. These are sampled in order with the Latin hypercube approach in order to optimally sample this input space. And on those, and we will run 10 times the number of parameters single column model from which we compute metrics, and this will serve as a training dataset on which we compute an emulator based on Gaussian process that allowed us to compute the metrics for any value of the parameters. And the good thing with this statistical tool, it's actually also give you an uncertainty associated to this metric. Once we have that, we can extensively explore the parameter space with emulator and quite rapidly. And we can compare that to the reference metric. And the good thing with this tool, it's actually take into account the different sources of uncertainty, the reference error that we provide here with the LES ensemble, the emulator error, and the structural error of the model. And by this comparison, we are able to discard all the impossible values of the parameter, and we can iterate the methodology to remove progressively impossible value. And in fact, this iteration is needed in order to improve the efficiency of the emulator. So we developed this tool specifically for this LES single column model comparison, but it can actually be used for other configuration. And I will try to illustrate the possibility of this tool with 3 different examples. The first one is the calibration of the parameters involved in a given parametrization. So here we focus on the radiative parametrization of the ECMWF, ECRAD. And the first thing we need to obtain is to get reference metrics for radiative computation. And so to do so, we developed a path tracing library for flexible implementation of Monte Carlo algorithm in cloudy atmosphere. I will pass the detail, but it allows you to compute reference for 3D cloud radiative effect in any 3D cloud scene of LES. So it is applied offline on 3D LES field, and it provides you some reference computation of 3D radiative effect. And here you have some, it can also provide you some virtual images, and you have a few illustrations here. And so what we did is we sample various LES cloud scenes that you can see on the upper left of the screen. Those are all cumulus cases, and we applied this Monte Carlo radiative computation to get the reference metric of the cloud radiative effect. For each LES scene, we also derive 1D cloud profile, and we run ECRAD offline so we are able to run ECRAD offline with the right cloud information. And so we aim at calibrating parameters involved in the cloud representation of the cloud geometry in ECRAD. And so on the lower panel, you have one example. It's the difference in top of atmosphere reflective shortwave flux between the parameterization and the reference. In blue, it's one configuration in the ECR which does not take into account the 3D radiative effect. In orange, one that take into account the 3D radiative effect without tuning. And in red with tuning, and you can see that actually, this is an illustration how we can use this tool to actually tackle together calibration issue with parametrization development. The second example use output for the climate model of the CNRM, ARPEG, and the objective is to illustrate you how we can use this tool to disentangle calibration issue from structural error. So here we aim at reproducing a very stable cases of very stable boundary layer cases, the Gables 4. And so in orange, in red, you have the standard version of the climate model, and this is the time evolution of the potential temperature at 8 meters. And blue, and in black, you have various LES result from these same cases. And you can see that the model is not able to reproduce the strong cooling that occur during the night. You can also see that on the middle panel that shows the vertical profile of the potential temperature. And you see also here that the climate model does not reproduce shallow enough, stable and cool enough boundary layer. So we looked at the value of 7 different parameters involved in the turbulence scheme that are listed here. And we have used 4 metrics, the potential temperature at 2 vertical levels that are indicated here at a given moment at 3 in the morning, and 2 levels of the wind speed vertical velocity, also at 1 in the morning. And so we only use 4 instantaneous metrics, and using that and using different iterations. So in yellow, you have the first iteration. So you can actually see that some values of the parameters allow you to reproduce some of the feature observed in the LUF. And actually, after the 9th iteration, the blue line, you can see that we have reduced enough the space parameter, and we are able to strongly constrain the behavior of the stable boundary layer throughout the night, although we only used instantaneous metric at a given time and only at 2 vertical level for the potential temperature and 2 vertical level for the wind speed. I will just use this case to show you one result where we evaluated the emulator ability. This is a figure a bit difficult to understand, but here we want to plot the parameter space, which has a 7-dimension parameter space, and we actually plot it into 2 parameters at each time. So each subplot is a projection in 2 parameters. So here, for example, CM and CE, and the color indicated the percentage of remaining space on the other parameters value. So on the left, you have the result obtained from 10,000 single column model simulation, and on the right, the result obtained from the emulator, and you can qualitatively see here that we have a very similar result. And the last example I want to show you today is how this calibration tool can be used both from 1D calibration to 3D calibration, and how doing a 1D calibration can accelerate your 3D calibration. So here, you have 4 cases of dry and cloudy convective boundary layer. On the upper panel, you have the vertical profile of the potential temperature, and on the lower one, the vertical profile of the cloud fraction. The black line is the standard version of the climate model of LMDZ. The blue line is large eddy simulation, and the color range correspond to the different iteration. In gray, the first one, in pink, the third one, in yellow, the seventh one, and in green, the 30th one. We have varied 9 different parameters implied in the mass flux scheme, the cloud scheme, and microphysics, and using 6 different metrics. And you can actually see that after the 30th evolution, we have strongly reduced the possibility of the vertical profile, and we have something that is quite in good agreement with the LES. Still, you can see some structural error. For example, on this figure, you can see that the maximum of the cloud fraction is located much lower than the LES, and that changing any parameter value actually does not act to improve this aspect. So once we have done those 30th iteration in 1D, we can run 3D runs and look at the behavior of those global model. And so here you have one figure that shows the zonal mean of the short-wave cloud radiative effect as a function of latitude. The black line are the observation, and the red line are the result of the 3D model using input value from the 30th waves of the 1D calibration. So first, you can see that already you have a good behavior of the 3D model after 1D calibration. And actually, we added 2 supplementary waves. And so in green, you have the result after 2 waves using a 3D radiative metric, global ones, and also mask region of top of atmosphere of upward fluxes. And you can see that you still are able to improve your model. So to conclude, we have developed a new tool that allows to accelerate model development. In fact, it harnesses machine learning to improve physical parameterization instead of replacing the physical parameterization. It strongly rely on the LES single color model comparison and allow to benefit from the complementary use of multi-cases with various metrics. Here, I think it's really key to continue developing parameterization and model, and this is really a tool that allows to accelerate the process. This tool is available freely under the link written here. And actually, I only have illustrated a few use of this tool, but you have other ones. So first, it can provide you a sensitivity analysis looking at the impact of each parameter, although you vary them jointly. It allows you to quantify parametric uncertainty and can also identify parameters that limit model performance. It allows you, I illustrate that, to disentangle model formulation deficiencies from calibration issue, and it can provide you some guidance for global tuning. And eventually, we can apply it to individual parameterization or all of them together, as we do when using a single column model version. This is contribute to a process of defining global tuning strategy with solid physical basis, as we emphasize on processes using single column model LES comparison, and statistical basis using the uncertainty quantification tool. And maybe the main message to keep is that it allows to tackle model development and calibration together. There are a few aspects that deserve further attention when using the tool. The definition of metric is a key step. And so it's important to define metrics that address the main biases of your model. It's not so easy to decide when to stop the iterative processes, as this impacts the evolution of the emulator uncertainty. It's not so easy also to determine the tolerance to error of your model, but actually, when you play with this tool, you actually better understand your model and it actually contribute to defining the structural error of your model. And eventually, it's still strongly, when using this tool, you still have a strong need of modeler expertise. I will finish here. Thank you for your attention. I've just given a few references, and I'm happy to answer your question.
So thank you, Fleur. We have time for maybe one question from the chat. Milan, Clover, would you like to ask a question, or maybe you have two questions?
Yeah, absolutely. There's really good reasons why parameterizations in a weather or climate model should actually be stochastic instead of deterministic. So not just one value, but for like every time step, you basically sample another value with some kind of like time and length correlation scales. So could you use your tool also to not just find, let's say, the best estimate for a given parameter, but also like a distribution you should sample from in order to maximize some kind of metric in the sense of like stochastically perturbed parameters?
So this is a very good suggestion. I was thinking that this tool, because the result of this tool is not just one given parameter value, but a space of the possible values that still give a consistent result with a larger dissimulation. I was thinking that we could use that to give some input to, for example, ensemble prediction. I was not thinking of stochastic parameterization, but it's actually a good point. Like it could be a way that we know, for example, that the three values of the turbulence should vary in a given parameter space, and we could sample each time one value. I never thought of that, but I think this is a good suggestion.
Thanks, Fleur. There are more questions in the Google Doc, but maybe in the interest of time, you can answer them in the chat.
Yeah, I will answer them directly. Thank you.
Thank you, Fleur.
Now, is by Anima Anandkumar. I think she's online now, and she's from CalTech and NVIDIA, and she'll speak about Fourier neural operators for fast weather modeling. Are you online, Anima?
Yes. Can you all hear me?
Yes, we can hear you.
Great. Yeah, great to be here virtually. Hope you're enjoying the event in person in Barcelona. So today I want to talk to you about the framework of Fourier neural operators, how it can capture fine scale features and have the ability to learn in a grid-free or a discretization-free manner, and how that has been really powerful for fast weather modeling. And after my talk, Karthik Kashinath, who's my colleague from NVIDIA and part of many of the works that are present, will dive deeper into the weather application and the benefits these methods are demonstrating there. Yeah, so indeed, I'm sure this audience needs no motivation that extreme weather is rapidly rising across the globe, and we need accurate predictions of such events, and as well as ultimately even climate predictions over the next few decades. And so the question of what machine learning can do in this domain, I think, is a very important one. And that is right, almost, it is a necessity, because if we go with the current numerical models, this is not just tenable. Because we want to go to the climate domain, which is much harder than the weather one. You'll see that later on I will focus on the weather application. But ultimately, to go to these climate applications, we require the ability to model these stratocumulus clouds. And that, I know, according to a paper by Tapio Schneider and his colleagues, would require about 100 billion times more computing than available today. So this is a necessity that we need the power of machine learning to hopefully get us 1 million times or higher leap in our ability to do accurate modeling of these turbulent processes. And the idea is this, power of the machine learning algorithms, in addition to accelerated computing such as GPUs and the scale up and out on powerful supercomputers, that would be a powerful combination to get us out of this requirement of computational burden of numerical methods. So what is the intuition that machine learning can give us such amazing gains? So if you think about these numerical models, because these phenomena are fine scale, and this fine scale, has an impact on the end outcome, it's a multi-scale phenomena, you have to have very fine discretization. And so this computational burden is inevitable for numerical methods. On the other hand, in machine learning, we are learning features that are data-driven, that are learned from large amounts of data available. And we do have large amounts of data in the weather domain. And from that, we can hopefully get better representations where we can avoid this fine discretization and time stepping, which is needed for numerical models. So that's the promise, and let's see how we can enable this, right? What are some principled machine learning methods that can enable this? And we also need to think about how this combines together with large amounts of data as well as large model sizes. We've seen in language models, for instance, the ability of GPT and other models to write human-like text, even though there may be sometimes inconsistencies. On average, you at least have coherent paragraphs and long pieces of text now being generated, which I think is really amazing. And at the same time, we do have lots of data available. So this combination of data, large deep learning models with computational infrastructure of GPUs can be a powerful combination. And in addition, the other benefit is with machine learning based models, we can do mixed precision. And that means our supercomputers can go a much longer way. We have better hardware efficiency than the numerical methods that require extremely high precision, especially for these applications that are looking at fine scale phenomena. And I think that's an added advantage of how with machine learning, we can learn better representations. We have the expressive power of large models such as transformers that can learn the features directly from data. And we can use mixed precision and other hardware optimizations to really kind of be also making the best use of our computational capabilities. With all this in mind, at NVIDIA, our CEO Jensen Huang last fall at GTC announced the Earth-2 effort, that includes building a supercomputer of unprecedented scale, better hardware capabilities, but at the same time, not having better algorithms for machine learning that can simulate ultimately the digital twin of the Earth and have good uncertainty quantification, good scalability to capture even fine resolution phenomena. And with such speed-ups, we can indeed enable better uncertainty quantification because we can have now lots of ensemble members. Typical weather models are constrained by the bottlenecks of computing, so there's usually tens of members, but we can easily do thousands of members or even higher because inference on these deep learning models is extremely fast. And at the same time, I think the other important tool we can provide to the weather and climate community is the scenario generation. If we can answer what if questions, right? So, and quickly generate different kinds of scenarios. What if you change these conditions? How would the scenario pan out? What would be the rollout from these new conditions, new forcings? And that ability can ultimately help us look at different policies for climate change mitigation in a fast manner. So these are all benefits we can derive once we have fast emulation models. And so this is our forecast net. This is the result of using the Fourier neural operator on weather data. And what you can see as a quick visualization is the ability to capture these atmospheric rivers quite accurately over very long ranges, right? These are thousands of kilometers. And so it's able to capture that well and do such prediction over several days to even a week or so. And so this is unprecedented for a purely data-driven deep learning model. So we have not incorporated any of the physics, and we've only used the data, and it's able to do this, which I think shows the power of the features that deep learning can run. So as a quick summary of what we did with ForecastNet, we trained it on the ERA5 dataset, and I'll describe the Fourier neural operator method that enabled this. And as I said, this is unprecedented for a machine learning-based model. We have about 8 times higher resolution than any of the previous deep learning works. And I think this ability to capture high resolution images and the fine scale features effectively by Fourier neural operator is an important aspect of this capability. That is what I believe is the core that has enabled such accurate weather predictions. And we can do thousands of ensembles in a fraction of a second, which I think is really powerful. So depending on how many ensembles you do and how you kind of choose this, you can get up to 4 or 5 orders of magnitude of speed up. So, up to 100,000 times speed up over the numerical weather models, which I think is astounding. And you also get a much smaller energy footprint, right? Sustainability is an important aspect when it comes to computational loads. And I think, this is also a great argument to using deep learning. So now I want to give you some insight into what is unique about Fourier neural operator and why can't we just use one of the standard neural networks, maybe UNet or transformers that are already developed in computer vision? Why do we need something new? So here the argument is, if you look at standard neural networks, they're designed for learning functions in fixed dimensions. So you assume images of a fixed size or a fixed resolution. And between training and testing, you don't change that. It's always fixed to the same resolution. On the other hand, if you try to run the model at a different resolution from training data, its performance is usually very bad. And on the other hand, the neural operator learns mappings which are in function spaces. And why is this important for applications such as weather? So here, ultimately there is a continuous phenomena and we are discretizing. So we don't want to fit to just the resolution of the input data. We want to ultimately be able to learn the fine scale continuous phenomena that are, whose signal we are sampling from this discretization. And so we should have the ability to generalize across different resolutions, across even different shapes of meshes. So you see, if it's an airfoil, you would use a different grid than, say, something just a square surface. So this ability is missing in standard neural networks. And I do think this is a huge limitation, because it'll only learn the phenomena at that discretization and not try to learn the underlying solution operator if it's a partial differential equation, or the underlying continuous phenomena that go beyond just the discretized data. And so that's where our Fourier neural operator is a new paradigm that enables such discretization-free learning. So here, your input can be, for instance, if it's learning partial differential equations, it can be initial and boundary conditions, and the output can be the solution function. In the case of the weather modeling, it can be the input conditions, and then the output is the conditions in the next time step or next several time steps. So that's the mapping we want to learn, and we don't want to just limit to the discretization of the input data. And so how do we enable this? So the way we think about this is solving an integral operator or a global convolution but through the Fourier transform. So trying to do a global convolution in the continuous space is very expensive, right? Because you have to go to very fine discretization, and that is expensive. That's what numerical methods attempt to do. But we won't be doing that. Instead, we'll go to the Fourier domain. We'll learn the weights in the Fourier domain. In fact, some numerical methods also learn coefficients in the Fourier domain, right? And come back to the input domain. But the difference is we'll compose such layers with nonlinearities. So that enhances the expressive power of these models. And you're learning everything in a data-driven manner. So it's combining the best of what we know from signal processing and deep learning together. So, and this is also discretization free, because you can solve this Fourier transform on different grids at different resolutions. So that's also the benefit we get. And by only keeping low frequency modes when we filter out, we are learning the overall spectrum through nonlinear transformations, while not being too dependent on the input resolution, because we'll only keep the low frequency modes here. And so these are some simple principles, but they go a long way to giving us the power of these, the ability to do these global convolutions, capture global correlations with Fourier transform. And with several layers of nonlinearity, we have expressive models. And with the ability to only by keeping only low frequency modes, we're also making this grid free or discretization free, because we will not be dependent on the input resolution. So irrespective of what the input resolution is, as long as it's high enough, right? You cannot have too low a resolution, then there is no learning. So you want some minimum resolution of learning. And then after that, it can also extend beyond to new resolutions. So this is just the reminder that the Fourier transform, right, solves convolutions efficiently in the frequency domain. And also the other benefit of using the Fourier transform, it's global, right? So it incorporates global correlations, whereas standard convolutional neural networks have a small receptive field, they're local. And this is really bad for global phenomena such as weather, right? So you want to capture these correlations across the globe, especially for longer term predictions. And I think that is an important aspect that these models are able to capture. And this is kind of an intuition of what these Fourier neural operators are doing. So they're effectively trying to compute this integral transform, like I mentioned, this convolution operation in the continuous domain. And so they're approximating this through the Fourier transform. And this composed with nonlinearity can now approximate any nonlinear operator, right? So think of now neural operator as extension of neural networks to infinite dimensions, to function spaces. And so this is now a new paradigm from standard neural networks. And I think this is very important to capture the underlying continuous phenomena and not overfit to the discretization of the input data. And so this is the result we see. This is the fluid flow equations, Navier-Stokes equations. So we trained only on low resolution data, like I mentioned, right? And we directly evaluated how it works on higher resolution data. And you see that it's still able to capture this. And we can also see this in the frequency domain, that it's able to extrapolate to even unseen resolutions, higher wave numbers than what is in the training data, which is not an ability with standard neural networks like ENES. And so I think this is also important that we don't just limit to our training data. We want good generalization. And to me, generalizations in terms of the higher resolutions is really important for all these kinds of physical phenomena. Yeah, so, we talked about these neural operators. So there is an interesting connection with transformers. As you may be aware, transformers have revolutionized language and now also are making a big impact in computer vision. The idea is they're much more flexible than convolutional neural networks, and they're more global, right? So you're taking patches of data and you're learning how to mix them together in what is known as self-attention. So you're looking at how different patches in the image are related to one another. And so we use this backbone, and for mixing across different spatial patches, we use our Fourier neural operator with certain special design of weight sharing. And so the reason we did this is now it becomes much more scalable. So if you try to do Fourier transform on the full resolution data, you cannot fit this on one GPU. And that is, we could down the line do fancy model parallelism. But for now, we wanted to have something that was scalable as well and give us the ability to still capture the fine scale phenomena. So we combine transformers with the Fourier neural operator to get the best of both the worlds. And so with this connection, we trained this on the ERA5 dataset, and given the initial condition, we wanted to predict the next time step condition and then ultimately do an autoregressive process to predict over several time steps. So Karthik will give you more details about the specific training and the benefits we saw with the Fourier neural operator in the weather application. So what I want to also show is a few other applications, such as carbon dioxide storage. So this is a multi-phase flow phenomena. And what we've been able to do is use these Fourier neural operators there with a big speed up. And so this is in collaboration with Sally Benson's group at Stanford as well as Microsoft. And so I think climate change mitigation is an important aspect. And using these tools to do quick simulation and assessment of what are good sites for carbon storage is something that can be enabled. We've also worked on coronavirus and the molecular dynamics there. As it invades a cell and undergoes replication, there are conformational changes, and we're able to track those conformational changes. So stress prediction in materials, it's a multi-scale phenomena. You predict the deformation and then the stress. And so we used these neural operators, in fact, even a simpler PCA-based neural operator in the fine scale, and get a big speed up. we're able to do very high resolution simulation of computational lithography for the first time. So I think so many applications of FNO, and it's great to see the impact of speed up and sometimes even better predictions because of the data-driven manner, which could be an issue with physics-based models that have modeling errors. But indeed, we don't need to limit to just being data-driven, right? And that's where the physics-informed neural operator combines best of both the worlds. You can also add physics losses if you like, and combine that with data. And we can also pre-train the operator and then test time, solve on a specific instance we want. We can further fine-tune that. And so with that, we also see good ability for learning. And with this, the benefit is we don't need the ground truth solver when it comes to solving partial differential equations. And so we can be very data efficient, or, is this essentially a self-supervised learning method that can be beneficial in many applications. So far, we haven't applied this in the weather application, but I do see moving forward that combining some of the physics with data-driven approaches can help us now go to even seasonal or sub-seasonal scales with our weather models. So we are productionized all these models through NVIDIA Modulus. It's open source. It's both in PyTorch and TensorFlow, and it has good hardware optimizations. You can use that out of the box. And you can also ultimately connect this to Omniverse for good visualization. The visualization I showed you earlier of ForecastNet was in Omniverse. So I think kind of like it's a nice platform for having all these capabilities be put together, and quickly you can get started on that and start using. So I encourage you to go look at the documentation, tutorials. I think this will be hugely helpful. Yeah, so I thank you for this opportunity. I'm really excited on what machine learning is able to do in weather and climate sciences. And I do believe thinking about principled algorithms such as neural operators and asking how we can learn in a discretization or grid-free manner has really helped us push the boundaries of performance for weather models and many other applications. Thank you.
Thank you.
So Balaji, yeah, we may have time for one question. Peter, do you want to go?
Yeah, I can do that. So thank you very much, Anima, for the very interesting talk. Great as always. Just one question, which is, you motivated at the beginning that you wanted to go in particular for shallow convection, and you wanted to basically represent shallow convection as well in the process. And then the question is, like, what is the data that you want to use to kind of learn shallow convection? Because we typically, observations are scattered, LES models are not general, and global models don't reach this resolution. So have you thought about this?
Yeah, that's a good question. And I know, to be honest, right, I don't know the answer. That's where I'm looking to you and the other experts on what is the relevant data, right? And there is also, but another question that we are exploring is, how do we learn indirectly? So if we directly don't have the supervised data, is there a way to learn from, right, like kind of, if we don't have fine scale data, but we have this coarser scale, can they still inform us? And can we try to predict the fine scale phenomena, maybe with the use of some of the physics, right? Like the PINO approach. But yeah, I agree. That's a hard question. And I'm curious your thoughts on that as well.
Thank you.
Yeah.
So thanks. I think we need to move on. Anima, there's another question in the chat if you'd like to respond in the Google Doc.
Okay.
Thank you.
Thanks, Balaji. Yeah.
Jean-Claude?
Before we enter the final discussion, is by Karthik Kashinath, and he will refer about Earth 2 initiative, which we heard a bit already, but not very much. So probably we'll have more detailed presentation. Are you with us, Kart? Yeah, you are. So
Yes, I am. Can you hear me?
we hear you, and the floor is yours.
Thank you. Okay, I hope you can see my screen.
Yeah, it's not full screen. We're seeing it with, yeah, now it is. Thank you.
Okay, great. Thank you. All right. Well, thanks to everyone for sticking it out to the end of this long day, and I'm glad to be joining you virtually at the start of the day here in California. And Anima set the stage for how Fourier neural operators can be powerful tools to learn the complex dynamics of weather and climate data. And in this talk, I'd like to dive a little more into the details and also connect it to some of the things that Peter Dueben and others have highlighted earlier on today. So I'll start with this slide that I grabbed actually from Peter's talk just a couple of hours ago, or less than that. And thanks, Peter, for setting the stage on what the challenges are for machine learning in integrating it with HPC and weather and climate applications. So just quickly revisiting some of the key challenges and arguing as to where we are today with our work here at NVIDIA in collaboration with several others. So one of the first challenge that was highlighted was different philosophies and tool sets. And I think we're already making significant progress in combining the philosophies from the machine learning side and the physical modeling side, as Anima described. And we've developed a lot of tools, including Modulus, to enable this. The second was off-the-mill tools are not sufficient, and I fully agree with that. And the Fourier neural operator is one example of how we use a principled physics-based approach to develop these machine learning models. Of course, there's more work to be done, but I think we're making progress on combining physics with machine learning. The integration is certainly difficult, and I think this has come up a few times in previous talks as well, and this is work in progress, which is why it's in yellow. The reliability challenge is a big one, and I think there's many groups working on this. There's an entire NSF AI Institute that Amy McGovern leads on trustworthy AI, and all of us are, of course, thinking about how we actually make our results reliable and useful, ultimately being used for predictions of extreme weather and also climate change. And then the sort of HPC challenge of scaling up to petaflops, I'd argue in this talk is something that we're already making good progress towards, and I'll show you some results. So just listing out the series of challenges, and this is a very long list. We've seen some really impressive results in the last year or two on machine learning methods for weather. We're starting to see some progress on climate, but really, as Anima highlighted, the key challenge is how can we predict climate change with any level of confidence, and in particular, extreme events as the climate changes. So that is one of an extrapolation problem. So machine learning, of course, is very good for interpolation, but struggles with extrapolating to unseen situations. One of the questions earlier today was exactly this. And there are some ways to combine physics with machine learning to help extrapolate to the future. Physics, of course, extrapolates because physical laws are designed to obey in all regimes. Physical consistency and causality is another big challenge. And there's a lot of work that's going on here. The LEAP program led by Pierre Gentin is looking at many of these challenges. Uncertainty quantification is a big one. We've seen that there's many diverse potential futures given all the uncertainties in the pathways, but also in the physics and our characterization of the physics. So this is another big one. Data fusion and assimilation is increasingly becoming a challenge, especially with non-conventional data sources coming in and on very different grids, and some of them unstructured, different quality, noise, etc. Scale up and scale out is another big challenge. Of course, the HPC workshop that we're all part of is addressing this. In terms of the approaches that machine learning offers, today I'll focus on multi-scale spatiotemporal modeling using the adaptive Fourier neural operator that was described by Anima. But we've also seen some work on super resolution segmentation in the machine learning world, which is also known as, I guess, detection and tracking in our world. Online learning to learn with new data sources that are coming in. And I'd say a largely unexplored area is reinforcement learning. And I think there's some really exciting opportunities there for RL, which I'll try to describe as I get towards the end of the talk. So the focus for the next 15 minutes or so will be on ForecastNet, which is the model that we've developed here at NVIDIA in collaboration with folks at CalTech, Lawrence Berkeley Lab, and several other universities. It's a global, data-driven, high-resolution Earth digital twin for extreme weather. Now, that's a bit of a mouthful, and I'll try to break it down as we go through the talk. So once again, grabbing another slide from Peter Dueben, he described that one of the biggest challenges, the single most important development to achieve progress in this intersection of AI and HPC for weather and climate science is how we can combine domain scientists with machine learners to have these sort of machine learning domain scientists. And I'd like to argue that our work here has been in that direction. We've been working closely with machine learners, with HPC experts, with software engineers, but also with domain scientists to kind of create this network, this group of people that can exchange knowledge and together produce something that's larger than the sum of the individual components. So this is the team, and I'm representing a fairly large group of people here. This is across various different institutions, as I mentioned, Lawrence Berkeley Lab, CalTech, Purdue, Rice University, and several other places, and of course, NVIDIA. So diving into the details, ForecastNet, which stands for Fourier Forecasting Network, is a deep learning model that essentially learns the dynamics of weather data and attempts to predict the future evolution of the system. The architecture is the adaptive Fourier neural operator architecture, which Anima described. It combines the power of transformers with the Fourier neural operator, and it's efficient and scalable. I won't get into too much detail, but the basic idea is that you have a Fourier neural operator that achieves spatial mixing very efficiently. You have global convolutions that can be represented in the Fourier domain with just a handful of modes. And this is much more efficient than using any other technique for achieving the sort of global convolutions. There's various other features to this model, and I encourage you to check out the paper, which was recently published on arXiv for the full details. The inputs are a series of two-dimensional fields at various different levels in the atmosphere, representing different physical processes, including the dynamics, so velocities, temperature, so a little bit of thermodynamics, some humidity variables, as well as geopotential heights and total column water vapor. It's a purely data-driven machine learning model at this point, and we are working towards combining it with Pino, the physics-informed neural operator approach. As Anima mentioned, that can really help us move to finer scales and also capture some of the physics more accurately. The current model is trained on the ERA5 reanalysis dataset at the native resolution of 0.25 degrees. As I mentioned, we have a list of variables at different levels in the atmosphere, a total of about 20 variables. We're also extending this to include more variables that represent radiative processes, vapor transport, clouds, and so on. The training set was from 1979 to 2015, so about 35 years of historical data. Validation is 2016 and 2017, and the held out test set is 2018 onwards. So getting into how exactly the model is trained. So we have basically an auto-regressive model. So the model takes in all of these two-dimensional fields at a certain time step and predicts that at the next time step. In our case, the time step is 6 hour data, a 6 hour time step. We also have a fine-tuning part of the model where we predict the second time step, so 12 hours ahead, and we actually tune with the predictions at both 6 hours and 12 hours. So we have basically a loss that combines these two. We have a precipitation model which is separate from the main model, and it has the same backbone as the standard model, but it basically takes in all of these fields at k, produces a k+1. This is the backbone. And then we use these 20 different variables that are predicted at that time step to predict the precipitation at the same time step. So we have a separate model that predicts the precipitation, and of course we compare it against the actual data. And in inference, we basically have these 20 vectors, 20 tensors that are then predicted over to k+1, and we have the precipitation model. So let me describe some of the results from this modeling approach. First of all, focusing on some of the fine scale phenomena, we're looking here at the initial condition here on the top. In the middle is the prediction from ForecastNet 96 hours ahead, so 4 days ahead. And in this case, we're using the ground truth to be the ERA5 data set. And once again, this is a test set, so it's not seen this data before. On the left, we have an inset that focuses on the West Pacific. And you see in the initial condition, the dynamics of the wind field. And then 96 hours ahead, we have a typhoon, Mangkhut, which was one of the most destructive typhoons in the Pacific. That's captured very nicely as you can compare. You can compare the ERA5 ground truth to the ForecastNet results, and you see that the size, the shape, the location, and in the paper you'll also see the spatiotemporal evolution of this hurricane, of this typhoon, was captured accurately. Now, if we look at the Atlantic on the right, here we have the initial condition. We're just starting to see these sort of tropical storms forming off the coast of Africa and heading towards the United States. And we see 96 hours later, we have these series of hurricanes, very rare events, Florence, Isaac, and Helen, all heading towards the east coast of the US. And ForecastNet, our model, captures these three hurricanes quite accurately, and also their evolution. So focusing a little more on hurricanes in particular, we have this example here of Hurricane Michael that was forecasted by ForecastNet. And as Anima mentioned, because these models are extremely fast, you can generate very large ensembles. So in this case, we have a 1,000-member ensemble that we can generate and characterize the uncertainties of the hurricane trajectories. And we see that our model captures the hurricane trajectory quite well, and the actual ground truth is within the uncertainty bands of this prediction. And if we look at the images on the right, we see over time from 18 to 72 hours, the dynamics of the hurricane as shown in the 850 hectopascal wind speeds are also captured quite nicely. You will notice that there is some smearing out of the fine scales, and this is something that we're working on. This is a sort of grand challenge for many machine learning models to really capture the most fine details of these data sets accurately, and this is work in progress. So let me show a video of ForecastNet in action and focusing here on hurricanes once again. So here we're looking at the integrated water vapor fields, which of course captures the dynamics of weather systems and moving across the globe. The FNO, our model predictions are in the open contours. The ground truth is in the solid filled contours. The NOAA forecast uncertainty cone is the white cone, and the actual track is in red. And we see here that the Fourier neural operator, the ForecastNet model, predicts not only the path of the hurricane accurately, but also captures the dynamics, the size, shape, and intensities quite accurately. So it's quite promising that on short timescales, we have a powerful model that can predict hurricanes and atmospheric rivers and various other extreme weather events. Of course, the challenge is to push this to longer timescales. So focusing on some of the quantitative results for these short-term forecasts, here I'm showing on the left the anomaly correlation coefficient, which is a measure of forecast skill as a function of time. And just to re-emphasize, the ground truth here is still ERA5 and not observations, and this is of course something that we're working towards. But if we look at the prediction skill of our forecasted model in red and the IFS in blue, we see that at short timescales we're actually doing better than the IFS when compared to the ERA5 ground truth, and then comparable beyond about 2 days to IFS. So this is really promising that a purely data-driven approach is already approaching the operational skill. And here on the right, we're looking at precipitation fields. As we know, this is one of the most complex fields to predict in weather and climate. The global field is shown in the middle, the initial condition, and 36 hours ahead ForecastNet predictions, and the ground truth ERA5. And if we once again focus on specific regions, the inset on the left shows the initial conditions across the US and in particular the western side. And we see at 36 hours, there's this atmospheric river that's captured very nicely by ForecastNet, including the shape, size, and also the landfalling location. On the right, we're looking at the European region, and here we see, again, the initial conditions has a bunch of features, and then 36 hours later, we have this large extratropical cyclone that's heading towards the UK, and that's captured also very nicely by ForecastNet. So let's look at the predictions globally, but also locally, focusing on the Western United States. If we look at the video on the left, we see the global total column water vapor dynamics captured quite nicely by ForecastNet. You'll see, all of the dominant features, these atmospheric rivers, extratropical cyclones, tropical cyclones, including some of the fine scale dynamics that are being captured. There is a smearing out issue. As I mentioned, the finest scales are not captured accurately, and this is something that we're working on as we speak. On the right is focusing on the Western United States region, I guess the East Pacific and the Western United States, and you see there are these large atmospheric river events which are responsible for 50% of the precipitation in California. And that is also being captured quite nicely by ForecastNet, at least at these lead times. So ForecastNet, because it predicts a wide range of fields, can also be used for wind energy applications. So here we're looking at the surface winds predicted U10 and V10 over a 72-hour period. And we see here that if we just focus on the land surface, the United States, we see that ForecastNet captures the dynamics of these complex wind events over mountain regions like the Rockies, in the wake of the Rockies, and over the Midwest and so on. So having accurate predictions of wind fields at these timescales is actually very beneficial for wind energy planning as well. Now, the grand challenge, of course, is extreme events. And here we're looking at the percentiles and the total precipitation predicted by ForecastNet versus IFS and Aero5 at the highest percentiles. This is a log scale going out to 99.99 percentile. And you can see that, of course, it's a challenge for both numerical models as well as machine learning models to capture the most extreme events accurately. And we see the ForecastNet underpredicts some of the strongest extremes, and we're working on this. And we hypothesize that the smearing out of the fine scales is one of the challenges here in capturing these most extreme events. On the right is the same plot for winds, and we see here that actually ForecastNet does a pretty good job of capturing extreme wind events quite accurately, and is getting quite close to the ground truth. Now, if we look at the short-term forecast scale on a few other variables, U10, Z500, and 2-meter temperature, Z500 geopotential height at 500 hectopascals. And once again, comparing ForecastNet in red versus IFS in blue, it's quite impressive that this purely data-driven model is predicting with reasonable skill out to about 8 days and getting quite close to the IFS model at these timescales. At Z500 as well, we see a similar result. And of course, temperature being a slow timescale variable, we have even better skill out to about 8 days, and ACC stays above 0.5 out to about 3 weeks. Now let's compare against the state of the art, and I must say that we haven't included results from Ryan Keisler's work with graph neural networks, which I guess beats Wayne et al. From 2020. But if we just focus on comparing against DLWP, the model that was developed by Dale Duran and folks at UW and Microsoft, that's the model that's shown in black here, and that was the state of the art until recently. And our model here is in red. We see a pretty significant improvement, and we attribute this to both the powerful Fourier neural operator approach, but also the higher resolution. We have an 8x higher resolution, 25 kilometer versus 200 kilometer, and then IFS is in blue. And then on the right is the RMSC, so the errors are also lower compared to the DLWP model. One thing that I should note is that the DLWP is actually quite stable and can predict reliably or close to reliably at S2S timescales. And this is an interesting opportunity to potentially combine these models that are powerful at shorter timescales with models that have longer timescale predictions. So maybe there's a combination of DLWP with ForecastNet that we could think about, sort of a 2 timescale approach to get to these S2S and beyond timescales. Now, this is an HPC workshop, so I want to spend a little bit of time focusing on the computational performance of the model and some of the scaling results. So Anima mentioned this, and I just want to re-emphasize that our model is about 44,000 times faster than IFS compared to a sort of node-to-node basis. Of course, there's a lot of caveats here. We can generate a 100-member ensemble forecast in a few seconds, and you know, we could go to a 1,000-member ensemble at the same time scale because you could just parallelize this across many GPUs. So we have very efficient ensemble forecasts. The 100-member ensemble consumes only about 7 kilojoules, which is about 4 orders of magnitude smaller in terms of energy consumption, and as I mentioned, about 4 to 5 orders of magnitude faster than NWP. So with this sort of footprint, it's very compelling to think about how machine learning can be used in conjunction with NWP, potentially to characterize the uncertainties better, to also make predictions more accurately, and so on. There are a few caveats, which is that ForecastNet right now is not physics constrained, and this is something that we're working on. And the second is, of course, that we don't predict the full state vector that IFS has. So we have much fewer variables and pressure levels than IFS, but that's also something that we're extending. So recently, in the last couple of months, we've scaled ForecastNet out to large scale. And I just want to show a preview of some of the scaling results and characterize the scalability of this model. So we scaled this model efficiently up to about 4,000 GPUs on 3 supercomputing systems, Jules Booster at the Jülich Supercomputing Center, Perlmutter at Lawrence Berkeley Lab, and Selene, which is at NVIDIA. And here are the scaling plots for the 3 different systems. The instance sizes correspond to the model parallelism. So we go up to model parallel 8 on Selene, and we achieve up to about model parallel 4 on Booster and Jules Booster and Perlmutter. We can see that the model scales very efficiently out to almost about 2,000 or so GPUs, and then it starts to taper off on Jules Booster. There is still perhaps a kink and maybe a scalability beyond that on Perlmutter and Selene. And this is quite compelling in terms of the scalability, because we can now start to work with much larger data sets and also train on much finer scales. The peak performance achieved was 140 petaflops in mixed precision. Again, as Anima mentioned, these models, machine learning models, can work with much lower precision than NWP, and this is a huge advantage in terms of being able to push to higher resolutions and achieve greater speed as well. The second plot that I want to show on the scaling results is that using both model and data parallelism, so hybrid parallel models, we were able to basically reduce the training time from about 24 hours, which was what we had on about 64 GPUs, down to about 67 minutes. So that's about 24 times reduction in the training time, and this is quite significant because this gives us basically the ability to train on much larger data sets on large systems. So looking ahead towards some of the scaling challenges as we head to higher resolutions, I just want to emphasize the key challenges on what it would take to actually scale these models out to 5 kilometer or even 1 kilometer resolution. So the first point I'd like to make is that, as Anima mentioned, the AFNO, the adaptive FNO, which combines the power of transformers with FNOs, have much better scalability than the traditional FNO itself. And I won't get into the details of the actual complexity and parameter counts, but you can look at this in the paper. And if we look at how this model might perform, extrapolating out to 5 kilometer data and 1 kilometer data, there are a few key parameters. The first is the sequence size n. As you know, in transformers, these can be very large sequences, especially in vision transformers. In our case, the size of the sequence scales as the dimensionality of the system. And D is the embedding dimension of this model. In our case, it's about 1024. And as we go to larger resolution data, it's likely going to increase as well. And K is the block count of the model. Apologies that we're not getting into the full details, but I would refer you to the paper to really understand what the significance of these different parameters are. So if we look at the current model with ERA5 data, we have about a sequence size of 1 million. The images, the two-dimensional physical fields are 720 by 1440. So already fairly large scale.
Could you get to the conclusion, please?
Okay.
I'm
right.
sorry.
Sorry.
Could you conclude soon, please?
Yeah. Yes, I will. All right. You have to take my word for it that we have to deal with very large FFTs as we get to much larger resolutions, and so this is one key challenge. And the second is large matrix multiplications and many matrix multiplications. So those are sort of the two key computational challenges. So I'll skip this slide in the interest of time, and I'd like to conclude with basically the looking ahead part of this. So there's a lot of exciting challenges looking ahead. So we're looking at extending this with embedding physics using PNOW, extending to a full state vector, higher resolutions, using generative models for fine scales. We saw a lot of interesting work already on this, and also comparing against the diagnostics that the ultimate users care about. So maybe the final slide that I'll leave us with is how do we use this for climate prediction? And this is borrowing on Bjorn Stevens from his keynote at the GPC conference recently, where he looked at what would it take to combine these types of machine learning models, spatial temporal models, with numerical models that are run at 1 kilometer resolution. So here we're looking at, let's say, ICON that's making a 300-year prediction at 1 kilometer scale. This would give us an exabyte of data. And it's pretty much impossible to work with that large volume of data. So one way we could look at combining ForecastNet with climate models is to actually checkpoint the model at, say, every month, and then use ForecastNet with these initial conditions from these checkpoints to explore the trajectory in that 30-day interval. So we can look at predictions accurately for that 30-day interval, as we've shown, but we can also look at ensembles around that and so on. So by combining a model like ForecastNet with a very high resolution climate model, we can actually start to use these AI models to accelerate interactivity with the climate data and also reduce the volume from an exabyte to orders of magnitude smaller. So I'll conclude there, and apologies for the large amount of information, and I'm happy to take any questions. Thank you.
Balaji, did you select questions? I lost my co-chair. Okay, we have a few questions on the web. There is one question by Milan, maybe which I select a bit arbitrarily, about scale invariance. Could you comment a bit your questions?
Yeah, that was originally a question that actually also was for the previous talk, which was that as far as I understand it, once you train in Fourier space and you learn that basically the different interactions between the scales, theoretically I can think about this as that the model itself can actually learn scale invariance, which is like for simulating turbulence would be super important. Have you actually ever tested that? Because I think in the 2D test case that Anima in the previous talk showed, I would have expected smaller eddies to be within the bigger eddies, but there weren't any. And so I was wondering whether you've actually ever tested for this like physical principle of scale invariance.
And may I add that in the simulation, the slope of the power spectrum was not really comparable with the real slope of the power spectrum.
Thank you. Yeah, that's a great question. And yes, you're right that learning in Fourier space and learning the dynamics using the Fourier node operator, in principle, in theory, you should be able to go all the way down to the Kolmogorov scale if you've got enough of the inertial range in the data. I would argue that the examples that have been tested, that we've tested this on, don't quite have the entire spectrum captured. And part of that is because of the smearing up at fine scales. And so in principle, we are learning the dynamics of the entire spectrum, but because of the smearing out of fine scales, we are losing some of the information at the finest scales. So yes, in principle, we should capture this, but there is still some work to be done to really extrapolate out to the finest scales.
Thank you. I think we shall proceed and to the discussion. Balaji, are you back? No? Connection has been disrupted? Okay, so we can start and hope that Balaji will be able to join. He prepared, in fact, a few questions that we may address during the discussion. And I guess most of us have the Google Doc in front of us. Yeah, okay. So basically, the question is, speaking about weather or climate is not exactly the same issues at stake. Of course, we all know that. But the question is, what about classes of machine learning? Are there some methods which are more intended to work for weather problems and some which are more intended to work for climate problems? Is that a question that somebody would like to comment, either on in the room or remotely?
I could take a stab. I'm sure there's many perspectives on this. I'd say that, you know, with climate, as I mentioned, it's an extrapolation challenge. And sure, with shorter timescale events as well, you can see, you know, extreme events that had never been seen before in the weather data. But with climate, we know that we are getting into a regime that has never been seen before. And I think the only way we can really extend out to such long timescales is using the physics. So we will have to leverage what we know about the climate system and bake that into machine learning models in effective ways to really extrapolate out to unforeseen climates. And I think Peter showed one of the recent works by Tom Buechler and collaborators. They have some really novel ideas on how you could use renormalization of different physical variables, so going from specific humidity to relative humidity, for example, as one way to collapse things into a common distribution. Of course, this may not be possible on all physical phenomena, but we would have to use techniques like this as well.
On the same issue of climate versus weather?
It's in some sense the same issue. Have you ever tried to test, to take two models, train ERA 5, and then try to do forecasts with two different models? Because physically, they should do exactly the same thing. There are bugs or whatever inside, or slightly differences. But in principle, your forecasting must work with both models because you're looking for physics and not for patterns. So you have a very clear way of validating that you really look for physics and not for patterns. I know from medical image processing of multispectral pictures that even if you're fully physically based, that it doesn't work when you change renders of the observation thingy. So the question is clearly, does that work with the forecast models?
Well, that's an open question, I'd say, because we haven't actually integrated the physics into these data-driven models yet. There are examples in simpler systems where the physics does help. We have some work on Rayleigh-Bennet convection and kind of more simple systems in turbulence, where we see that if you bake in things like the spectral behavior of the system or maybe, you know, conservation laws, you do see an improvement in the performance. So one could hypothesize that we might expect the same with the weather situation. But at this point, we don't actually have results to prove that.
I guess a proof of the pudding would be to run CMAP simulations and to actually train those forecast models for different CMAP scenarios as well. Train on basically pre-industrial and apply them for different scenarios and compare them against the CMAP results. And just on the general question, yeah, clearly there are some applications that will only work for weather. There are some applications that may also work for climate. Weather is absolutely much simpler in a sense that you don't need to extrapolate so much. But also there are machine learning solutions that will almost certainly work for climate in extrapolation as well. If you think about more like regression type models and stuff like this, you can actually learn more of the physics as well. And also for those machine learning solutions that may not be able to extrapolate, we also know that we can, for example, if you talk about emulators, we can actually also train our model emulators from simulations of climate change scenarios and so on and so forth. So it's not that weather is possible and climate is impossible. It's more like weather is doable easily and kind of the nice playground to make progress, like Karthik did with ForecastNet. And the climate is kind of the bigger problem where we really need to be careful. And whatever we do, we need to be aware of the fact that we can't extrapolate easily.
Yeah, I mean, I guess also from like a modeling perspective, I mean, it's good to figure out kind of whether or not current methods generalize to the degree that they generalize or not. And then B, like I think of my job as a machine learning researcher is to create new models that do this. So, you know, actually what would be super helpful is actually all of these critiques, because, you know, like I'm writing this down in the background, and like that is the thing that, like, understanding the pain points rather than saying like, oh, everything is promising. I think like we're getting to the point where some of the things look promising, but we need, I don't know, like much stronger, like, I guess, diagnoses of these things. And so we can understand the degree of nuance and limitation such that we can push the new models forward. I don't necessarily think this is an either or situation. I think different models have different inductive biases, and like we should think about that in terms of the problems that we have.
If I may be a bit of a simplistic, I mean, when you deal with weather forecasting, especially at rather close lead times, basically you have to deal with uncertainty at the initial state. And then machine learning approaches might have quite a superiority with respect to advances in time. And we've seen, in fact, on one slide that the accuracy of the machine learning-based forecast was much better for the first hours. Of course, when the lead time does increase, it goes the other side, the other way around. I mean, the physics-based model it's better than the machine learning. Now, when you speak about climate, and specifically about climate change, you try to understand and foresee what will happen in a future which is completely unknown. And then, for me, using only very refined statistical method like machine learning is not enough. At least you have to inject some physics. And maybe physics-based machine learning method would then be much more suited for climate. Once again, that's a quite simplistic view, but maybe it can help to bring element of replies to the question. Other remark on this issue?
On that note, maybe, I mean, it's also the question, what does a machine learning tool actually do? Does it just provide you a statistical answer for a specific question, like what the forecast looks like in 5 days from now? Or does it actually represent the three-dimensional atmosphere and you go forward with it? And then, I mean, most of the zeroth order approaches to kind of do something like weather bench type scenarios would probably build a statistical model that the way you basically see that the solution would smear out if you kind of go to day 10, for example, of the prediction, and then you would clearly not represent the atmosphere in all its beauty, but you basically represent a statistical mapping procedure and get good results for mapping. But this may not be very good for climate predictions. But on the other hand, if you, for example, take the work from Zuman and others with the generative modeling, you actually go closer to a model that actually learns to represent the physical dynamics and to be kind of still keep sharpness for long forecast lead time. So we kind of, it depends a little bit on how you view the mapping procedure that you're doing. And we're getting there in a sense that we are getting better in actually building atmosphere model rather than statistical tools that just go a couple of days into the future, for example. And also, I mean, as you say, clearly, the more physics we can put into the model, the more trustworthy the results are, in particular for climate simulations. And there's also a lot of progress. So we still have a long way to go, but we are getting there and kind of building more like atmosphere model rather than actually just statistical mappings.
Yeah, I had actually just a simple question to the last speaker. So what happens if you just iteratively run your model for 30 years? What kind of climate do you observe then?
Yeah, I wish I could actually run it out to 30 years. It turns out that there are instabilities beyond 3 weeks that actually lead to explosion of the results beyond 3 weeks. So as I mentioned, the model is not stable on long time scales, and that's why we're looking at combining something like the DLWP model from Dale Duran and folks that are more stable on long time scales, along with our model on shorter time scales. So just like you have, numerical instabilities in physical models, there are instabilities in machine learning models as well that lead to blow up. So yeah, unfortunately, we don't have climatology out to 30 years.
That sounds pretty good to me, because it looks like you're hitting somewhere the deterministic bounds, or you're in the smearing of the deterministic bounds. And that's something which is, how to say, a point of view that you really see physics. But it will be fun to overcome this.
Yeah, I agree. Yeah, in fact, there's some nice work by Noah Brenowitz and others that look at kind of a stability theory analysis of these machine learning models when you couple them with physical models to see what types of instabilities might form and how they might lead to basically blow up. So I think, yes, we could definitely leverage a lot of the tools from numerical modeling and the theory of PDEs and so on to look at how these models behave.
Okay, the second question that was prepared on the Google Doc is maybe a slightly similar, at least as some some resemblances with the former one. Deterministic versus stochastic machine learning. The question is this fundamentally a stochastic problem, so that deterministic methods are limited? What do you think about the stochastic versus deterministic?
If I may, so the entire problem of weather and climate predictions is fundamentally a stochastic problem in its nature. So that's nothing special for machine learning in principle. I mean, we always have stochastical problems, if you want, at hand. The thing is that a lot of the machine learning techniques actually turn out to be quite good in representing those uncertainties. So if you, for example, think about those GAN networks that we applied now in a couple of places, or other generative models, they are actually kind of quite able to learn the uncertainties of the mappings that you have and to generate, for example, ensembles of your forecast. So Karthik can easily change this model probably from a deterministic one into a kind of a model where you can run an ensemble and then not only 20 members, but maybe 2,000, because it's kind of dirt cheap. And they are very good at actually representing those uncertainties. And also, uncertainties are also kind of quite good for machine learning in principle, because typically, I mean, in a lot of hybrid applications, and we haven't talked too much about hybrid applications here in principle, but you can also combine machine learning very well with existing models by learning the errors, for example. And the errors are typically quite nonlinear. They're typically very difficult to describe with conventional tools, because otherwise you could just get rid of them anyway. And you can learn them because you can measure them as well. So machine learning tools are actually also very able to learn errors and therefore also to represent uncertainties that we have in existing models. So it's just, I mean, I don't think there's a big difference. I mean, weather and climate predictions will always be stochastic and probabilistic to some extent, but and machine learning is no specialty here, but machine learning tools are actually kind of quite capable of targeting this problem of error predictions and uncertainty representation.
An argument which makes machine learning as well difficult, because you train it with erroneous models. So the picture the machine learning is presenting is the same as the erroneous model you have originally.
Well, if you train from the model data,
exactly.
yes, you're right. Yeah, but obviously you can also train against observations, for example, right? I mean, it depends on what you're training, right? On the specific machining problem you have at hand.
Okay, I just got a mail from Balaji. He said that it was what, 6:30, and said he has an urgent commitment which could last half an hour. So he should be back with us pretty soon.
I'm back now, Jean-Claude. I just got back.
Oh, here you are. Fine. We discussed the first two questions, Balaji, that you prepared, in fact, about climate and weather and deterministic versus stochastic. So I don't think we are going to start the discussion again on these two issues, but maybe you could relay with before the last question about the explosion of machine learning and workforce. Can you introduce the question and lead the discussion?
Yeah, so I think Peter even mentioned it in one of his slides. So one of the reasons anybody can now get learn a little bit of ML, and the tools are just amazing. They're very high quality and they're very widely available. I'm sorry to say the same cannot be said for domain models. And how do we fix that? I mean, we complain, domain scientists tend to complain that machine learning is a black box, but I can tell you a GCM is a black box also. So, yeah.
Yeah, I think one comment I wanted to make on this is, I guess fundamentally because a lot of people, especially with deep learning, have come from academic science and usually had like a GPU or two, most of the problems that you deal with are like on a much smaller scale, right? Like I don't have an HPC cluster at my disposal, so like the tools for a GCM would be hard even if you made some of the tools available. So I want to, I guess, say like some of the availability is also because philosophically the hardware has been easily attainable by like a grad student myself. Like when I was a grad student, like I was able to write like a one-page document and get an NVIDIA K40 for like my own personal research use. And that was very helpful. I think having access to similar type of hardware in this domain seems much harder from the people I talk to, but you can correct me if I'm wrong.
Yeah, but more than the hardware, I was just saying, you can start writing a notebook and say import keras, and then you're off and running. And you can't do the same with models. So,
yeah, if I could comment on that specific aspect of being able to, write and play with these models. There's definitely some nice work coming out of AI2, what was previously Vulkan climate modeling, Oliver Fleur and company developing GT for Pi, and basically a domain-specific language. So that I think is really significant progress towards making these models much more interactive and usable, writing in Python and so on. So I'd like to be able to see that sort of approach extended to other climate models. Of course, there's also similar work with LES. I think Kyle Pressel in Tapio Schneider's group previously had written this PyLES, which made writing LES codes in Python for stratocumulus clouds and so on. So I think there's a few examples out there, but yeah, as a community, we're yet to move in that direction as a whole.
From my perspective, there's the good news is, oh no, let's start with the bad news. The bad news is that the model as we build them will never ever be as simple and kind of easy to code up like neural networks are. Basically because the algorithms that are behind deep learning are just that simple. I mean, if you compare it, they're really easy, and you can easily build very powerful neural networks also with kind of just to-do loops in Fortran that can basically also learn weather bench type problems. So it's not really very fair to compare because the domain science models will never kind of be able to be that simple to some extent. But on the other hand, as Karthik says, we're kind of going into this direction anyway, and we are actually kind of quite forcefully going to this direction. So if we turn our model now into the Python world, for example, at ECMWF, we are flipping FVM into a Python code built based on GT4Pi. We're going to work towards domain-specific languages where we basically try to abstract the complexity of all those operators away from the domain scientists and make it actually easier to kind of write code in the sense of an equation rather than a very complex do-loop structure. So we're doing the right things, and we have to do the right things. We're also porting to GPUs and accelerators and make it easier to kind of port the next generation of models. So we are kind of going towards the right direction, but it's a long way, as we know, a 10 years way at least, I guess. And we will never get even close to the simplicity of machine learning tools in principle, just because the algorithms are much simpler in deep learning than they are in our GCMs.
So again, let me follow up on that, Peter. So I think somebody possibly Niels put up a comment earlier in one of his slides where it's a provocative comment from Dale Durran. I don't know whether you should take it literally, which something to the effect that it's time to do away with the die-core. So if you're saying that the machine learning is intrinsically simple and GCMs intrinsically are not, then is that the direction we should go? We should do the Dale Durran thing?
Well, I think I had it on my slide. Yes.
Oh, you had it. Sorry. Yeah.
So I think my personal answer is I still don't buy it in the sense that we will get rid of those models, for example, for the simple reason that you need still. I mean, we have observations that are kind of sparse. You only have very limited amount of information that you can actually get from a satellite in a 2D picture, for example, and not like a 3-dimensional picture of the atmosphere. So we will still need models in the future. But this doesn't mean that we need, for example, to run everything with our models that we have in 3D. So I think those models that are learning straight away from observations, even or just from model data or even reanalysis data, they will find their place. I mean, I'm sure so my personal answer would be the future is hybrid, that we will see more and more machine learning tools happening and appearing, but we will still need those 3-dimensional models for process understanding, for running very long time scales into the future, and to basically make physical ground predictions, and to also fill the state space, because the observations that we have are basically really very, very sparse. So we're talking about models that have billions of degrees of freedoms, and we're talking about observations where we have a couple of millions maybe that we can actually use per day or something like this. So the dimensions don't really fit to each other. So I think the future is hybrid.
Yeah.
I also
easy in expressing themselves, so that's the contrary today. People in the room have difficulties in finding a spot to speak. So Luis, finally.
Yeah, I have quite a lot of comments. So one is about the comics from Peter. It's very interesting because as far as I know, most of the physics parts is already machine learned stuff. It's only done with the techniques of the 19th century, like least square linear fits, which is a type of machine learning. The other thing is programming the models in Python and saying GT4Pi is just incorrect because it's only a wrapper around it and the kernel is C++. So be careful. And the C++ inside of GT4Pi is so complicated that I'm pretty sure that here in the room there might be half or a quarter of a person understanding it, or even less. So that's definitely not really helpful. And the other thing is, of course, if you replace something which is already machine learned by something which is machine learning, you can make quite some progress, because today you can do it much better than a simple least square fit. The problem I see is that it will be extremely hard to get the dynamical core and the turbulence into account. And another question I have is, in how far with the FFT methods you see the smearing out potentially as an aliasing process, so that you push energy in the shortest wavelengths and that you smear because of that. That's normally what happens in models, why they do truncations when they go into some kind of Fourier or spectral space. And it's not a problem of the process itself.
A lot of points. Maybe I can comment on the first one. Is basically the GT4Pi. Yes, obviously. I mean, it doesn't mean that we are there yet. I said we have a long way still to go. But it's definitely kind of, we're going into this direction in terms of simplifying the code that the domain scientist is seeing. That's what I argue for. But I'm not saying we're there at all. The other thing was
the dynamical core are scientists as well, and they think the dynamic core is not that complicated.
Well, that's what people in Hamburg used to say, that you can fit a dynamical core within 50,000 lines of code or something like this. That's not the reality that I see in ECMWF, but maybe there's a discrepancy here. And the other thing about physical, I mean, obviously you're right. There's a lot of machine learning happening already if you kind of count regression techniques and parameter fitting and these kind of things into the machine learning world, which I would probably do. But this doesn't mean that there's not physical knowledge inside the model tuning, for example. So if we upgrade our cycle, there's a lot of physical knowledge going into every single change that we do to our model forecast system. So it's not that we basically just do only machine learning or something like this. We're not even close. We do a lot of, if we get a bias in the tropics, for example, for temperature, we do physical reasoning and to try to understand what the problem is coming from. So it's not that we are just doing machine learning.
The tuning parameters are the parameters of the model where you don't have any physical clue on. That's why they are there, because otherwise you would replace them by some physical expression.
Yeah, I disagree.
Okay.
Yeah, I mean, I think the other thing too, maybe to frame this a little bit, is I guess the question is, if let's just say we're doing weather prediction. I think for each question, it should be, given my compute budget, what is the model I should use to get the weather prediction that I want to get? I think what's interesting about sort of the newer deep learning approaches is that with a far more limited compute budget than you would get at ECMWF or something, you get something that is reasonable-ish and is also pretty widely available. And if we think philosophically from the point, like, you need one big system that solves all problems to one where people can do specialized weather prediction because there's hardware everywhere, maybe that changes the question slightly in terms of like the types of questions that we can answer, the type of desiderata that we need to satisfy, because like, you know, if you're you, Peter, like there's a lot of desiderata that you need to satisfy, but if I care about, is it going to rain on my walk to lunch, and I want something very specific, the compute budget I would need for something like that is way, way smaller. So I guess I understand maybe like the philosophical tension, but it seems to me that there's like more possibilities open rather than like one supplanting the other.
In the moment of silence, is there a machine learning method that can do advection solver? Is that true? I don't know about the Dale Durant's talk, but is there a solver which can do that?
Well, you can think about doing something like this, yes. I mean, basically what Karthik and others are doing is you learn the equations to some extent, right? And the question is like, how much can you actually find back specific components of the model, like advection, for example, in what we do with kind of machine learning there, and how much is it basically just the magic working in the background? But in principle, yes, you could think about working on advection, learning, for example, advection schemes and stuff like this. And people have suggested this, and people are like, for example, the work from Stefan Heuern goes also in this direction, where you basically try to update the fluxes in a sense using a machine learning tool to basically improve your representation of subgrid scales, and by basically doing advection schemes, as far as I can tell. So there are ways of doing this, but the question is like, how often can we actually really understand what we are doing in a sense? Is this kind of just advection, or is it just learning the dynamical core? Or is it just also learning the physics scheme at the same time, or what are we actually learning? So it's difficult to distinguish.
If I can sorry, if I can interject to Peter. So if I understand what Dale Durant is arguing, and I'm looking at his paper, it's not just to learn the equations. He's saying that instead of using stencil operators, which is sparse linear algebra, you can use machine learning, which is dense linear algebra and works better on GPUs. So he's actually saying it's something which is not actually the same, if I understand it, as learning the dicore. He's learning flow without learning dicore. He's learning turbulent fluid dynamics without invoking Navier-Stokes equations.
Well, again, the question is like, what do you actually learn if you, for example, train from era 5? Do you learn the die-core, or do you learn the entire model, or how derivatives and subgrid scale schemes and so on? Yes, I mean, absolutely, yeah.
Okay, but can we proceed with the questions that you prepared for the discussion? Because time is running.
Yeah, we could, but I'll let Karthik, he was just about to say something and I interrupted.
Yeah, I was just about to add a comment that's relevant to what Balaji said and Peter and the previous comments. I think it really, I mean, what you're learning boils down to how you're testing the results. So what is your diagnostics to test the results? If it's only RMSE and ACC, then you're just looking at a purely, very basic statistical level, is the skill good or not? But if you start to look at a series of other metrics, let's say in a turbulent flow with the kinetic energy spectra and the Kolmogorov scales and the Taylor microscale and so on, you can then start to characterize, is this actually learning all of those multi-scale dynamics that we care about? So I think what we're learning, that question can only be answered from what diagnostics we use to test the results of the model. And I think this was already highlighted by Peter, but we really need to push towards a much more comprehensive set of diagnostics for our machine learning model predictions. And right now, I would say it's still fairly basic diagnostics that we use.
I agree with that. It's a good point. So maybe we can go on to another question, which is, is it one of our core skills, machine learning now? And if it's a core skill, how do we get the people who know the science and also know this core skill? Is there sufficient workforce development in the universities going on? What do we need?
I can add a comment. I mean, we have someone in the room. He's clearly a deep learning expert. So, and then Anima, of course, gave the talk earlier. She's also a deep learning expert. So I think we're already starting to see a lot of deep learning experts that are, getting engaged with the domain scientists. And I can't help but, if I could share my screen for just a second, I want to show Peter's slide. I think it was quite funny, but also captures things well. You see this slide?
Mm-hmm.
Yeah, so I'd say we're no longer stuck on the left. I think we're somewhere in this process towards heading towards the right. We are seeing quite a few machine learning people working very closely with domain scientists, and that line is getting blurred. I mean, myself, for example, I started off as a turbulence modeler and then went into weather and climate modeling and now doing a lot of machine learning. So I'd say I'm somewhere in between on the spectrum, and I think there's many others that are also there. This doesn't, of course, address your question about how we get more people of this kind, and of course that points to university education and tutorials and workshops and hackathons and various other things. But yeah, that's a first comment.
Yeah, I mean, I was going to turn the question on the head. If someone could write to me and tell me what are the things as a machine learner that I should learn in order to be able to do good domain science, I would love that. I think from an ML standpoint, it is, especially with deep learning, not all areas of machine learning are like this. It is very much an experimental science. So, I think everyone here has taken a linear algebra class that's kind of, unless you're getting into something very exotic, you probably already know all the math that you need in order to do this. And it's just a matter of like trying things out. I think the thing that's nice that when people have models on their GitHub repo, you can try to like retrain the model, try to do inference, whatever. And it's almost like an apprenticeship of just doing things. I don't think there's any like secret sauce, to be honest with you.
Mm-hmm.
Yeah, my take would be that you need both. I mean, you need machine learning scientists starting with the domain sciences, but you also need domain scientists starting to look into machine learning. And I guess the long-term trajectory should really be that we have basically machine learning used in the domain scientists. So it's not that we should have just the one machine learning group at an institute like ECMWF, but rather we should have machine learning applied throughout the workflow. So we should have a lot of people basically getting the knowledge of how to do machine learning. And we need the influx from both sides, but we also need to be a little bit careful about the domain scientists for domain scientists. So just to give you one example, for 2 weeks ago, we had the numerics training course at ECMWF, and the course was undersubscribed. And last week, we have the machine learning training course at ECMWF for the first time, and the course was 3 times oversubscribed. Mm-hmm. And we need to be a little bit careful here that we also still develop educating domain scientists for domain sciences in a sense. I mean, basically, at the machine learning workshop, I asked the audience a question like, what computing languages people should learn when they start. And basically there were, I think 98% of the people said Python and only 20% like Fortran because they could have more than one option basically. So we need to be careful that we don't end up with models with hundreds of thousands of lines of Fortran code, but we don't have anyone anymore to kind of look into those models as well. So while I'm in principle happy would say that we need more people working with machine learning and domain scientists and to kind of bring the two communities together, I'm nowadays also getting a little bit afraid of really losing too many people into the Python world. And it's just much more attractive to play around with a 500-line Jupyter notebook than with a 50,000-line dynamic core if you are a PhD student. So we also need to be careful there.
Yeah, it's a great point, Peter.
I'm sorry, I've just seen that we were also maybe supposed to discuss issues related to session 1 during that discussion, which neither Balaji nor myself understood. So if there are questions that relate to talks that we heard during session 1, and there are maybe questions, probably we should find some time to address them either today or the last morning if we have time, because there are some discussion slots also. But sorry, if we were supposed to discuss session 1 issues, we overlooked that and we didn't prepare for that. I'm sorry. Unless you have something to add, Balaji, what I would like to do now is to basically thank all the speakers that we had during the day, and especially during session 2, and all the people who participated very lively in the discussion, either remotely or on site, and wish you a good evening, and see you tomorrow at 9:15 for the coffee. Thank you very much.
Thanks for having us.
Thanks. Thank you. Bye.
So, sorry, before leaving, a very practical point. Could you please bring all the glasses and bottles to the library, please? We would appreciate it. Thank you.